In this video, I'm going to talk about StarkNet's Cairo language and its basic integer type, the felt. Felts are field elements because they belong to a finite field, and certain operations like division over a finite field can produce pretty weird results. So in this video, I'll explain what a finite field is, why it's being used here, and why these weird results actually do make sense. I'm going to start with an explanation of how numbers are represented in computers and how arithmetic operations are done over these numbers, as well as some of the trade-offs that are inherent there. Then we'll get into finite fields, first talking about sets, then groups and rings, which are sort of precursors to finite fields. Then we'll talk about the finite fields themselves and how Cairo FELTs implement and make use of these ideas. And finally, we will look at some Cairo code examples to see all of these ideas in action. So computers, as I'm sure you're aware, represent all data internally in a binary format. So whether you're looking at video, audio, text, numbers, or anything else, the computer will internally represent that as a collection of bits, where each bit, of course, can have one of two possible values, hence the by in bit. Because the computer doesn't understand the letter A or the number 5 or what a pixel is, what it understands is only 0 and 1. And actually, to be more accurate, the computing hardware, your CPU and memory, the actual machinery that underlies your operating system, your programs and all of that, this machinery that powers your computer, it doesn't actually understand 0 or 1 either, because it internally represents these values, 0 and 1, as high voltage and low voltage, not as some literal 0 and 1. Typically, the 0 is represented as a low voltage and the 1 is represented as a high voltage. So for example, if you were to zoom in on your computer's memory and you were to look at a single cell of memory, you wouldn't find in that single bit a 0 or 1, written into the computer hardware. You would find low voltage or high voltage. And the computer is perfectly happy to operate on these representations of 0 and 1. Everything works perfectly fine. We sort of overlay our labels of 0 and 1 rather than using low and high because 0 and 1 is more natural and it's easier for us to understand. So as I mentioned, all data is represented in this binary format. You can almost think of the bit as like the atom of information, like the information theoretic particle that all information is made of. You can break down any sort of data into a collection of bits. And this collection of these atoms, that's what the computer actually operates on. And one of the questions we can ask when taking this information theoretic perspective of computing is, how much information is there actually in a single bit or collection of bits? Obviously, in one bit, we can have one of two possible values. In a collection of bits, for example, if we have 32 bits, how much information can we store given this bit space? And it's pretty straightforward to figure out. In each bit, we have two choices, right? So in this bit here, there's two possible choices. In this one here, there's two, and so on and so on. So these multiply out. So the total number of permutations you can have given 32 bits will be 2 times 2 times 2, multiplied together 32 times, which is 2 to the power of 32. Or more generally, 2 to the power of the number of bits. So in this case, 2 to the 32 is about 4 billion. So there's about 4 billion different permutations you can have given 32 bits. And of course, if we were to have more bits, if we had 64 bits, we would have a lot more permutations. And the number of permutations grows non-linearly because each bit you add multiplies the total number of permutations by 2. So for 2 to the 64, we have 100,000, million, billion, trillion, quadrillion, 18 centillion or whatever is above quadrillion total possible permutations. Now, in the context of numbers, we may decide that our numbers are going to be 32 bits each. And then in that case, we could represent this many numbers, 4.2 billion numbers. So we could have, for example, 1 to this number, or if we wanted to start at 0, we could go 0 to this number minus 1. We have to minus 1 from the top end because we've added the number 0 to the bottom end. Or if we had 64 bits, we could represent this many numbers. And of course, the trade-off with using more bits is that it takes more space. And a natural question might be, why don't we do variable bit length numbers so that we could represent small numbers with, say, even 8 bits or say 32. And then if the numbers get bigger, we could just expand it out to 64, 128, and so on. And you can certainly do this, but you're just going to lose efficiency. It's going to be much more efficient for the computer to operate on, smaller fixed length numbers, especially given the computing architecture. So if you have, for example, a 32-bit architecture CPU, what that means is that the machinery operates on collections of bits that are in 32-bit chunks. These are called words. So the processor will naturally, in each computational step, it will be able to operate on collections of bits of this 32-bit size. And most modern CPUs are now 64-bit. So same idea, but they're operating on 64-bit chunks of data in each CPU step, in each CPU cycle. So what that means is that if our numbers are 64-bit in a 64-bit architecture CPU, the operations on those numbers will be extremely, extremely quick. You can't really get any faster. The CPU will be able to do an operation like an addition of two 64-bit numbers in a single CPU step, which is ideal. You could, in that scenario, have 128-bit numbers. There's nothing preventing that happening. But then when you're doing operations, when the CPU is doing math on those 128-bit words, it's going to have to take multiple cycles to do that operation. And it's probably not going to scale in a perfect way. So rather than taking 2 CPU cycles instead of 1, now that we've doubled our word size, you're probably going to have to add, the least significant halves of those numbers and then keep track of the result, carry it over to the most significant, do that computation, and then combine them at the end. And it's probably going to take quite a few more cycles than you might expect. So the efficiency is just a lot better if you can keep your numbers to the architecture word size. So our numbers are going to be represented with a fixed number of bits. Let's think about how we can actually map a given set of bits to a range of numbers. So here I've got an example showing how we can map 4 bits to different ranges of numbers. And I'm using 4 bits here just because it's easier to show. There's only 16 possible combinations, but the principle is exactly the same with 32 or 64 bits. So here are all of the permutations that you can have given 4 bits. We start at all zeros, and then we go to just 1, 1, and we count upward in binary all the way to the highest value. And the simplest mapping for this range of bit values would be to an unsigned integer. Like we could imagine that this is 0, this is 1, and we go all the way up to 15. There's 16 possible values, but we have the 0 there. So we can only go up to 15, not 16, because the 0 is taking up one of our positions. Now, if we wanted to have negative numbers, we could do a signed integer, and then we go from 0 all the way up to 7, and then we switch to -8 and count back down to -1. This might seem like a sort of weird way to map the negatives onto this range, but it actually makes a lot of sense. Look up 2's complement if you're interested, and there's very good reasons for why the range is mapped onto the bit range in this way. And you can think of it almost like the 1 place here being a negative sign, or even more accurately, you can think of this this leftmost bit being the -8 column. And if you look up 2's complement, that'll make a lot more sense. But in this situation of having a signed bit or a signed integer, we have the exact same number of total possible values, right? We have 16 possible values given our 4 bits, and we're just mapping, instead of 0 to 15, we're just mapping these bits to sort of a half positive and a half negative range. But we have the same number of points on the number line, so to speak. And I have down here kind of an illustration of the number line. So the unsigned int that just goes 0 to 15, you have this number line here. And the signed int, you can imagine it's just shifted over to the left in a sense. we have the exact same number of points. We're just sort of shifting over from the positive only, 0 to positive 15. We're just shifting that over so that we capture some of the negative values as well. Now we could then imagine mapping this bit range to a much larger range of numbers. So if we didn't care about the precision so much, but we just wanted to cover a huge range, we could do this sort of logarithmic mapping where we go 0, then 10, then 100, then 1,000, all the way up to 10 million. And we could also have negatives in there too, so we go negative 100 million. And here we're covering like a much, much wider range of numbers, but all we've done is expanded out the range that we're mapping, but we haven't actually gained more precision or more points on the number line, right? We still only have 16 points, and the fact that we've expanded it out, in a sense, it hasn't gained us anything. Like, you can't actually fit more information. It might seem at first glance like, wow, you can map such a huge range of numbers given this this scheme, but you still only have 16 points. So in a sense, you're actually literally not containing or capturing any more information in an information theoretic sense using this different mapping. And it's a similar thing with the float example. So floating point numbers are just a way to represent, decimal numbers that are not just integers in a computer. And so we can imagine mapping this bit range to, we have 0, we have 0.001, we have some decimal values. And then we also have a high range too. We go up to 1,000 and negative 100. So here it seems almost like we've captured the best of both worlds. We have a huge range and we have a lot of precision. But again, we only have 16 points that we're mapping onto this number line. So the fact that we've stretched and contorted the number line doesn't get us any more information. We're not actually doing any better in a sense. Floating point numbers they have their purposes for sure, but the amount of information being stored is completely and wholly determined by the number of bits you have. So changing your mapping, you in a sense aren't, you're not really winning out. You're not cheating the system and somehow capturing more information there. And just to give you an idea of how floating point numbers are implemented in computers, the scheme is something like this. So you'll have, here we have 32 bits, just like we had up above with the integer example. And instead of mapping all the way from 0 to that 4 billion, we take some bits and sort of set them aside for different purposes. So we have a sign bit at the leftmost bit. Then we have, a few bits for the exponent. Here's 8 bits that will do the exponent. If you think about like scientific notation, you have your exponent on the, you have like 5.1 times 10 to the 23. That exponent, we can set aside some bits for that. Then we have the mantissa, which is that like 5.2 or whatever. The like decimal part at the start there, you can set aside bits for that. So you can get a certain amount of precision there. Then you can have your decimal cover a wide range of exponents, both positive and negative. So you can get this big range of numbers and implement your floating point number. But as I said, in all of these situations, the actual amount of information we can store is determined completely by the number of bits, not the scheme that we use to map those bits to a given number line, a given range of numbers. Oh, one more point on these logarithmic and floating point number schemes or mappings is that it may seem like you have a lot of precision and you also have a lot of range, so you have the best of both worlds. But what you actually have is you have a lot of precision in the narrow range, or when the numbers are small, you have a certain amount of precision. Then as that exponent gets bigger, the gaps between your points on your number line that you can represent with your system, those gaps get bigger. So you lose precision as you go out on the number line. And that's because you have a fixed mantissa, you have a fixed precision to your number. And when that exponent is small, that precision is pretty good. Like those gaps between your numbers are pretty small. As this exponent gets very big, your precision is fixed. So as this exponent gets big, those gaps get bigger and bigger between your numbers. So you have this sort of nonlinear variable precision, which is fine for certain cases, but it can cause all sorts of problems, especially when doing mathematical operations on your numbers, which I will talk about now. Now let's go back to our integer example and think about what happens when we start to do math over a finite range of numbers. If we've got our range from 0 to 15 or the signed int from -8 to +7, and we start to do math over these ranges, we're going to run into the problem where suppose you have the number 15 in your collection of bits there, and then you add 1 to it, it's going to flip over to 0, which might not make a lot of sense. It might cause your program to crash. And similarly for a signed integer, you may hit the number 7 in this case, this small case, and add 1 to it, and then you roll over to a negative number. So you go from the most extreme positive to the most extreme negative in like one move. And this sort of integer overflow has been the source of all kinds of problems. And you do have certain programming languages will try to prevent this, and there's been lots of work to try to mitigate this kind of thing. But if you think about what the computer's actually doing, it does make sense for it to roll over. You know, like there's only so many things you can do if you have this fixed bit length. The computer doesn't really have any choice. It can't just expand to give you more bits on the fly. Instead, it will tend to do this. It will wrap around. It will stick to this scheme that it has. And when you reach the end of the range, like in this unsigned integer, it's going to flip over from the highest value in the range. It's going to flip over to the smallest. And so this gives us a sort of picture of the way integers are represented in computers, integers and other numbers, as more of a circle than a number line. You know, you can imagine these number lines being wrapped around into a circle because the computer has this tendency to not just, you know, give up and die when it hits when it's at the highest end of the range and you try to add 1 to it or you try to go beyond that. Rather than just freeze and crash, it just wraps around. And so you get this kind of circular number circle rather than a number line. Now I should mention perhaps that you can have higher level languages that do allow you to have really large numbers and not simply roll over. So Python, for example, doesn't have a hard limit on the integer size you can have. It doesn't just roll over when you hit a number that's too big. But underneath this, Python is still, you know, the operating system, the CPU is still operating on those 32 or 64-bit chunks. And given one of those little chunks in isolation, it will still roll over. But Python is using higher level, you know, tricks and algorithms to allow you to represent these really big numbers. But you're not getting around this fundamental thing where given a fixed length number, you're going to have to either roll over or just kind of stop the program when you hit that upper limit. Now this method of doing arithmetic operations over a number circle instead of a number line is what's called modulus math. So what modulus does is it just allows us to do our operations, but it keeps us constrained to our range of numbers. So for example, if we wanted to do something like 10 plus 7, in a normal number line, that's obviously going to give us 17, but that's outside of our constrained range. It's not inside of our circle. So with modulus math, we would, you know, solve that by starting at 10, and then we add 7 to that. So we can go 1, 2, 3, 4, 5, 6, 7. So 10 plus 7 modulus the size of our range, which is 16, gives us 1. And another way to think about this is modulus is sort of like the remainder, because you can keep going around the circle and the answer you get at the end is sort of like the remainder of that operation. You might go around the circle 20 times and then you land on 2. So it's sort of like your operation, take the answer you would get in a full number line, and it's like you're dividing that by the modulus range, in this case 16, and then you check out what your remainder would be. So given 16, for example, this modulus size of 16, if we took, you know, even what is the number 16 on this range, we're going to get 0. And you can think about that like it's like 16 times 1. The remainder is 0. And if we did 32, 16 times 2, or you could think of 32 as like 2 to the power of 5, that's going to be, that's going to pull us around the circle twice. And the remainder will be 0. So 2 to the power 32 mod 16 is going to be 0. Now, given our integer range and this modular math scheme, most of the arithmetic operations work fine, assuming you're okay with this modulus thing. And there's really no way around that. If you have a fixed number size, a fixed number of bits per number, you're going to have to do the modulus. And in many situations, it's actually fine and it works out okay. But given this number range, this integer range, and this modular math, we can do addition, we can do multiplication, we can do subtraction, and they all work pretty much fine. They just modulus the size of the range. But division, on the other hand, doesn't really work. You get sort of weird results when it comes to division. So we'll talk about that now. So I mentioned how addition works in a number line. Maybe I should mention subtraction and multiplication as well. I mean, it's just the same as addition, where addition takes you around the number line as needed. So does multiplication. So if you did 7 times 3 on a normal number line, that's going to be 21. On this modulus 16 thing, we're going to go, up to 16, and we want to get to 21. So 16, 17, 18, 19, 20, 21. So the remainder, 21 mod 16, is going to be 5. And subtraction just takes you the other direction. So if you wanted to, with the unsigned integer, it doesn't make as much sense because it's like 0 minus 1 is 15. But it makes more sense on the signed integer. You have the 0 here, and if you start subtracting, it'll just take you into the negatives. And, here the trade-off is it makes a bit less sense when you swap from, the highest positive to the highest negative. But again, you can't really get around that kind of thing with a fixed range of numbers. You're either going to have this situation where you go from the highest to the lowest, or you're going to have this situation where you go from 0 to your highest possible integer. But again, back to division. Division is where things get a bit weird, because if you're going to do division, for example, 1/3 on a number line, a number circle, like one of these, you don't really have your answer. What you'd like to arrive at for your answer would be 0.3 repeating forever. This is a truncated version of that, but you would like to arrive at a true 1/3, which is going to be 0.3 repeating forever. And that number is not on the number line. And in principle, or the fundamental problem is that you have this finite number range. And when you start introducing these rational numbers, these numbers that are, a ratio of two integers, you can have this massive, infinite, in fact, range of numbers even between any two numbers. So between 0 and 1 in this true Platonic rational number realm, there's infinite numbers between 0 and 1. So computers being finite, you're not going to be able to represent infinite numbers. And especially if we want to stick to an integer range, like this example here, like a signed int or an unsigned int, we don't have non-integer numbers. So when we're given the question, what is 1 divided by 3, what is 1/3, the best we can do in this kind of scheme tends to be to approximate it. So most languages will give you a truncated example or a truncated result. In Python, for example, you can do integer division and it will give you this kind of result. It will round down. So I just realized I made a mistake here. 1/3 is not equal to 1 in Python integer division, for example. The answer should be 0. But you get the idea. We have this limited range of integers, and we're going to have to map the results of our operation, this division, to one of our integers. So either 0 or 1, neither of those are actually correct. They're not precise in the sense of, it's not what we might expect the answer to be. And this scheme of doing division, this integer division scheme, it has this advantage that it does map to the integers. You can't really blame it. It's doing a decent job. The answer, sort of makes sense. It's close. It gets as close as it can, but it's not precise, and the algebra also doesn't work. So this is a property we would really like our number system and our arithmetic to have, is for the algebra to work out, especially when we're doing more complicated things and operations like cryptographic operations, we really want like a sound, solid algebra. And this integer division scheme breaks it. So if you take this expression here, x over y times y should equal x, right? Because the y's should cancel, and then you just have x and x on the left side, x on the right side. It should work out. If you sub in 1/3 here, so x is 1, y is 3, we get 1/3 times 3. And if you actually run that out using integer division, the 1/3 will result in 0, right? This is wrong. It should result in 0. And then times that by 3, you're going to get 0, which is not 1. Your value of x should be 1. So this algebra breaks given this kind of scheme. So we would like to find a system where we map to the integers, because that's the range we want to stick to, and our algebra works. Now, another approach to division would be float division. The problem here, of course, is that we're no longer in the integers. We're now using floating point numbers, and we may want to stick to our integers and not use floating point numbers, because floating point numbers have all sorts of problems of their own. They don't get away from this fundamental problem of having absolute precision and working algebra and all these things. But in a floating point division, we might get this kind of answer for 1/3. And the pluses here are that it does make quite a bit of sense. It's kind of what we would expect. Although because floating point numbers, like all numbers represented in computers, have finite range, a finite number of bits, you're going to have to truncate that number. So 1/3 should be 0.33 repeating forever. You can't do that in a computer, obviously. So you're going to get this truncated version, which is 0.333 a certain number of times, and then it kind of gives up. So it does make sense, but you're going to get problems when you start multiplying these out. This limited precision, if you manipulate these numbers enough, you will potentially run into problems where that limited precision actually gives you incorrect answers. But it does make some sense. Negative is it's not an integer. Positive is it's pretty precise, but it's not exactly precise, right? Like it's truncated, like I said. And the algebra may work. So if you try this out in Python or even in C, and you do like 1/3 and you get the answer and you multiply it by 3, it will tend to work out, but I wouldn't guarantee that things are going to work out in every situation, because ultimately the computer has this truncated, imprecise version of your number, and it's trying to like round up and down. So when you're doing, this kind of thing with 1/3 times 3, you might get 1, because it's going to take that approximation of 1/3, multiply it by 3, and find that it's really close to 1, so it rounds it to 1. But it might not work out, because you have this imprecise representation. With certain numbers, the algebra might not work out, so you shouldn't rely on it in like a mission-critical cryptographic kind of scenario. So finally, we get to Cairo division, and this is where the result of 1/3 looks very, very weird. If you try 1/3 in Cairo, you will get this answer, which is completely doesn't make any sense at first glance. We get this massive, massive number, when ideally we would like to have a small number, close to 0, like 0.3. But the advantage here, and I'll explain why it gives us this big number in a minute, but the advantage here is it is an integer. It's keeping us in our integer range. And given the stuff I'll explain in a minute, it is precise. This is, given our new definition of division that we'll talk about, this is exactly precise. And the algebra works. So when we use our new definition of division and we sub in our values, this statement actually does work out perfectly. And that we need these kinds of properties. We need this rock solid range of numbers where the arithmetic operations work perfectly over that range. When we're doing cryptographic applications, we need these properties. So these properties, again, as I mentioned, one is closure, that's staying inside our range of integers. Another would be absolute precision. We can't be truncating things. If you start truncating numbers and you're trying to do cryptography that's like mission critical operations, you can have failures. You can have people exploit this lack of precision and do bad things in your system. So we need that precision and we need that working algebra. And in this situation, the fact that it doesn't really make sense kind of doesn't matter. And I'll explain how it works and how it actually does make sense right now. So now we get into finite fields. So the TLDR on finite fields is it's a finite set of numbers that can do addition, subtraction, multiplication, and division without error. And finite fields are actually widely used in cryptography. AES uses them, RSA, ECC, which is elliptic curve cryptography, and Shamir's secret sharing, and many others, I'm sure, use finite fields because they have these great properties. And to understand finite fields, we should start by doing a quick refresher on what sets are. Sets are a pretty simple and foundational concept in math and are actually used as a foundation for all of math, where sets are sort of this bedrock core concept that then all the rest of the mathematical concepts are built on top of to make everything consistent and solid. And sets are just a simple collection of elements with no necessary operations defined on them, just a collection of things. And some of the more well-known sets would be the natural numbers. So that's the counting numbers, 1, 2, 3, all the way to infinity, sometimes including 0. Another would be the integers, which includes the natural numbers, but then we have 0 for sure. And we have the negative numbers all the way to negative infinity, the negative integers. Another would be the rational numbers. These are all of the previous two sets, and then also any number we can represent as a ratio of two integers. So, 1/2, 9/44, things like that. Then we have the real numbers, and this set includes all of the previous ones. And then also numbers like pi that cannot be represented as a ratio of two integers. Pi has that non-terminating, never-ending decimal expansion, and you can't actually capture that with two, finite integer values in a ratio kind of manner. There's no x over y that will give you pi, where x and y are integers. Then we have the complex numbers, which includes all of the previous sets, and then also these weird complex numbers like I, where I is defined as the square root of -1, which is a whole rabbit hole that we won't go into now. Then we have groups. So groups are basically sets with an addition and a subtraction operation defined for them. So this set doesn't have to be a certain range of numbers. It can be infinite, it can be finite, it can be one range or another, and it doesn't actually have to be numbers either, although we're going to deal with only numbers here. Groups are a very broad concept and are one of these really fundamental ideas in math as well. And groups are really about studying symmetry and all of these things, and it's a fascinating topic, but I won't go into that too much now. A group is this set, in our case numbers, where we have this addition and subtraction operation defined on them. And when I say addition, the term addition is used and the plus operator is usually used here, but we're not talking about regular old addition necessarily, because as I said, these groups can be the set that underlies a given group. It doesn't even have to be numbers. So we're obviously not going to simply do addition, like regular old addition in all of these situations. We just have to have this addition-like operation. And it's addition-like because it's a binary operation. You take two inputs and you get one result. And it has, especially in the case of numbers, it does function. Normal addition functions quite a bit. It has the properties that we would like to have for a group. So those properties include closure. We want our addition operation to take elements within our set of numbers and always produce an answer that's also in our set. So if, for example, we're working with this example here, where I've got the numbers, 0 to 99. So it's just similar to our previous examples where we had 0 to 15. So here we're doing our operations modulus 100. So for example, addition works perfectly fine as long as we have our modulus 100 in the addition. So we just do our addition and it wraps around the circle as needed and we get a result that's on our circle. So we stay within our set. So here, the regular addition operation that we're used to, given our set of numbers here, it works perfectly fine. And so for example, given our normal addition mod 100, we have 1 plus 1 equals 2. We have 99 plus 99 equals 98. That one's a little more weird, but again, we're just wrapping around, and we end up at 98 after doing this operation mod 100. So the addition operation, our normal regular arithmetic addition, works perfectly fine here as this binary group addition thing, because it has closure, like I just described. It has associativity, where it doesn't matter if we do this part of this expression first, add these two, then add C, or whether we add these two, B and C, and then A, the answer is the same. We also have a unique identity element, which is we would like there to be some element in our set, in our group, such that we can take any number A and add that element to it, and we still get A. So again, regular addition here works perfectly fine with a 0. So our group here has a 0, and our addition functions like regular addition, so we do have our unique identity element. We would also like there to be an inverse element for each element given this operation. So we would like there to be, for each A, there should be some B that I can add that will give me 0. Right? So I should be able to pick any number on this circle, and there must be some other number I can add to that, and it should bring us back to our addition identity operator, or our addition identity element, in this case 0, and that is the case. So for every number on this number line, this number circle, there's a number we can add to it that will bring us back to the top of our circle, back to the 0. And this requirement, or this fact here, having this inverse element, this also kind of gives us a subtraction, because we can imagine whatever this number is. So we have our number A, and we try to find something we can add to A that will give us 0. So if you had, for example, 23, you want to get to 0, you can add 77 to that. That'll bring you back to the top of the circle. And so you can think of, if A is 23, then negative A, the inverse of A, is 77, which might sound kind of weird, but if you have a number circle with negatives, it actually just works out perfectly. Like, if we have the negatives, then 23, the inverse for that, the thing that will bring you to 0, is negative 23. And if you flip that over to the unsigned integer circle, 23 is in the exact same position as 77, so it works out perfectly. But this gives us a sort of subtraction. In this operation, we get as long as it has these properties, we then have this addition and subtraction defined over our range of numbers, and when all this is satisfied, we have a group. So now we would like to expand the capabilities or properties of our group such that we have a ring. And a ring is very similar to a group. It's a set with addition, subtraction, and multiplication. So now we have an additional property on our set. So in the case of rings, the plus operator, that addition operation we just talked about, it has the additional property of commutativity. So what that means is that A plus B is the same as B plus A. And in the case of regular addition, like the one we were just describing, that of course is the case. This works out fine. So given our previous example here of 0 to 99 with the plus operator, that is satisfied. But then we add this additional operation entirely, which is sort of like multiplication. It's a binary operation where you have 2 inputs and you get 1 output. And we call this thing multiplication. We use this star symbol or an X. But it's not necessarily, in all rings, it's not necessarily regular old, arithmetic multiplication that we're used to. Because again, sets, these rings and these groups can have all kinds of things that aren't even numbers in them. But we use these symbols because it's multiplication-like. And this additional property needs to have closure. So just like the addition one, it has to keep us within our set or within our range of numbers. And regular multiplication, like regular number multiplication that we're used to, is going to have that property as long as we're doing the mod 100, which we will in this case. So that works fine. We then have associativity. So whether we do this A times B and then times C, or B times C and then A, we should get the same result in both situations, which is of course the case for regular multiplication, so that works fine too. And then this operator should also distribute over addition. So over our previous operation, this one should distribute over it, and A, times B plus C should be the same result as A times B plus A times C. And all of this works great in the case of this example, like I said, as long as we're doing the mod 100, and other than that, this operator will function just like normal multiplication. So now we go over to finite fields, finally. So finite fields are an extension of rings and groups where we have a set with addition, subtraction, multiplication, as just described, and division. So we also add a couple more properties to the multiplication operator. We have commutativity, where you can flip the order and the multiplication will work out the same. We then have also an identity element. So this is a multiplicative identity, some element in our set, in our range, where you can apply the multiplier, the multiplicative operator, and you get the number that you inputted. So like in the case of our numbers where we have this normal set of numbers, this would be 1. A times 1 is the same as 1 times A, gives you A, right? It's the element which you multiply by your number in question, and it doesn't do anything to it. You get the same result back. So we need to have an element like that, which we do in this case, in our example. We also want this zero multiplication property where if you have any A and B, which multiply together gives you 0, then either A should be 0 or B should be 0. There shouldn't be two like non-zero elements, where again 0 is that like additive identity thing where it doesn't do anything. You give it A plus this is 0 and it gives you A. I just remind us of that because it doesn't necessarily have to be the 0 that we're used to. But in the multiplication operation, you should have this property where if the only time you get multiplication bringing you to that additive identity is if one of the operands is that element, that additive identity itself. Basically, it functions like normal multiplication, where you would expect you have this identity, you have this fact where things multiplied together don't give you 0 unless one of them are 0. And finally, we have the multiplicative inverse. So this is division, essentially. This is where for each number in our set, such that that number is not the additive identity is 0, we have an inverse such that A times its inverse gives you 1, that multiplicative identity element. So, that's division, basically. Like we can imagine in like a floating point example, you have the number 5 for A, then you want to find some inverse of 5 that will give you 1 when you multiply them together. And of course, in the regular float example, that would be 1 over 5. 5 times 1 over 5, you get 1. Boom, it works. Now, given the example we've been working with our 0 to 99, what would the solution to this be? What is the number that we multiply 5 by to get 1? We can imagine we multiply by 5 by some number, it wraps around the modulus circle, and it brings us to 1, right? But in the case of the example with 0 to 99, this one is actually modified so it works, but in the example of 0 to 99, that ring of numbers, there's actually no solution to this. Because as you multiply 5 by whatever number, say you multiply 5 by 20, that gives you 100, which mod 100 gives you 0. So now you've landed on the 0. if you do the same operation times 5 times 21, you're going to skip over the 1. You're going to land on 5, right? So there's no solution here because the order, the size of the field, of the set that underlies the field, the size of the number of elements there is not a prime number. So you get these problems where if you have some operand, which is a divisor of the order of the field, then you won't be able to solve this. You won't actually have a finite field because you won't have a multiplicative inverse like that. Your division won't work. So the solution to this is to have a prime order. The size of the field should be a prime or a power of a prime, and then it all works. So if we modify our field here to be Z101, 0 to 100, now it's a prime number because 101 is a prime number. Now our previous question of what is the inverse of 5 actually has a solution, because 5 times 81, given this order, actually works out. 5 times 81 gives you 405, and mod 101, that actually brings you to 1. That actually works out perfectly fine. And because we have this fact, because in this case, in our finite field with our definition of multiplication and division, 5 times 81 is 1, we then have 1 over 5, this new kind of division operator, is equal to 81, right? And our algebra works. Given this definition, given this finite field, this algebra works out. X over y times y actually does give you x. So we now have the properties that we need to do important, like mission critical math that we can't truncate, we can't round, it can't be imprecise. We can now do these arithmetic operations perfectly over this finite field, and we can define and implement our cryptography on top of this, and it will work out perfectly fine. And just as a side note, a proper finite field will give us the discrete log problem, which you may have heard about. It's used widely in cryptography, and this is the problem of, given some number b, what number do I have to raise that to get a, given my finite field, right? So it's like, given this ring here, this field, I choose some number on here, and it's like, say I choose 3. Okay, now what number do you have to raise 3 to? What power do you have to raise 3 to get 99? And for this small example, it might not be that hard to figure out, but this is one of those really hard problems where it's very, very hard to find the answer. You have to almost just brute force it. There's some kind of shortcuts I think you can take, but it's very hard to find the answer, and it's very easy to verify a solution. So if I give you a solution, it's really easy, it's really fast to compute whether that exponent actually does bring you to 99. And this is one of those beautiful one-way functions which are very useful in cryptography. So this whole finite field thing, this is how Cairo FELTs work. This is why you get these weird results when you try to multiply or divide 1 over 3 in Cairo, you get this weird answer. This is because what it's doing is it's operating over a finite field. And the operations, the division, multiplication, they're defined such that we have a finite field. So the solution to 1/3, it maps to this weird number because it's using this fact of the modulus and the way we talked about how to define division, such that it gives you, it wraps around the modulus and it brings you back to 1. That's what Cairo's doing. So Cairo FELTs, you may know this, but they have the finite field that these FELTs belong to. They are of order p, where p is a big prime. It's 2 to the power 251 plus 17 times 2 to the 192 plus 1. So this is a big prime, and the reason for choosing this sort of weird number is that we need to have a prime order. This finite field needs to have a prime number of elements so that our division can actually work out, like I just described. And this is what's going on. So in a sense, the the way that Cairo is doing this, and I'll show some code examples in a second, actually does make sense. It makes sense given this finite field sort of thing. We achieve closure, we have absolute precision, and the algebra works out. So the finite field in Cairo for the FELTs, this is sort of what it would look like. This is a signed version. The unsigned version would be similar, except it just goes 0 all the way to p. Here we have 0 and then a positive side and a negative side. And the highest positive number is going to be p minus 1 over 2. And the greatest negative number is going to be the negative of that. So we actually have this nice, because the field is a prime order, it's obviously odd. So then we have this kind of nice bonus property where we have the positive and negative ranges are equal in magnitude. And we have our 0 in the middle there. So we have if we didn't have the 0, it'd be an even number of elements, but we have the 0, so it's odd, and of course it's prime. And that is how it's constructed. And finally, we'll look at some Cairo code examples. So here I've got a simple Cairo main function, and I've got p defined here. This is the big prime, and I have half p defined as well. More accurately, this is p minus 1 over 2. So this would be the largest number in the positive range. That's this one there, p minus 1 over 2. And we can print that out, and let's print out p, and that's going to give us 0, because when Cairo sees this big number, it's going to think about it like this. We're starting at 0, we have this huge number, so we wrap around all the way back to 0, because we're giving it a number that's the size of the entire field, right? So we can then see, we can get an idea of what the upper range, like what does this range here look like? The greatest positive number, the greatest negative number, and we can get an idea of where this number range, where this field flips from its greatest positive value to its greatest negative. We can get an idea of that by saying, printing half p minus, half p, then half p minus 1 minus 2, and half p plus 1 plus 2 plus 3. So that will give us this. So we can see this is the greatest positive number, and this is the greatest negative number. Note they're the same number, just the sign has flipped. So that's that very most southern point of that number circle where we flip from positive to negative. And we can see that as we're moving essentially clockwise along that circle, we go from 38, 39, 40. We've hit the maximum positive. Then we flip over to the maximum negative. And as we continue, we start counting down 40, 39, 38. And eventually we get back to 0. We get back to -3, -2, -1, and then 0. We can also have a look and see how this division works. So I mentioned that division is going to give these big weird numbers. So we can see, 1/2 gives us, it actually gives us the largest negative number in the entire number range. And that actually makes sense because, 1/2, given our new understanding of how Cairo division is going to work, where we need to, 1/2 needs to give us a number on our circle such that if we multiply that by 2, we get back to 1, right? We need to be able to have that fulfill this algebra, this one here, x over y times y equals x. So we need to have 1 over 2. We need to have that give us a result such that when we multiply that by 2, we get 1. And in fact, if you take this big number here, right, this is the largest negative number. So it's right on the tip here. It's right on like the southernmost end. And if you take that number and you multiply it by 2, you're already like halfway around the number circle. You're halfway around the number circle and then just a little bit over. So if you do that twice, you're going to do a full rotation and land on 1. So in that sense, this result as the solution to 1 over 2 actually does make sense. And it's a similar situation with 1 over 3. We want this to give us a result such that if you multiply that result by 3, you get 1. So here we have this number that's in the positive range, and it's essentially somewhere over like here. So then this is a point on our circle where it's like a third of a turn around the circle. So if we do 3 of those, we go 1, 2, 3, we wrap around the circle and we get back to 1. And then the situation is similar again, but a little bit different for a quarter. I mean, the concept is exactly the same. This is giving us a result such that if you multiply it by 4, you get 1. But here it looks a little bit odd because we have this negative number. So we've got, this is the largest negative, right? This one here, the top one. Now we have a negative that's about half of that. So that would be right about here. It's about a 3/4 turn around the circle. And so this 3/4 turn, when we multiply that by 4, we're going to do, so we've done 1 3/4 turn, we're here. Now we do another 3/4 turn, we're here. That's 2 of them. Then we do another one, that'll bring us here. That's 3. And then we do one more 3/4 turn, and it brings us back to the top. It brings us back to 1 in this situation, actually. And the reason that this question of 1/4 didn't bring us to kind of where we might expect it to be, which is like over here, a 1/4 turn, because a 1/4 turn and then times 4, you should be able to get back to 1. But because the reason it's doing that is the division isn't working out properly. There's essentially no point on the line here where when you multiply it by 4, it will bring you back exactly to 1. There might be a point on this side here, 1/4 turn, where you multiply it by 4 and it brings you to like 0 or 2 or something, but it doesn't hit quite 1. So then the way to get around that is you just try 3/4 turn, or you try some multiple such that when you do the multiplication, you actually get to 1 exactly and not something close to 1. So that is what's going on there. It's a similar situation with 1/5. And finally, just to prove to you that all of this works, you can actually take and do 1/2 times 2, 1/3 times 3, and you should see a bunch of 1s. So boom, it works. So yeah, that's how Cairo works. That's why the division looks the way it does, and that's how finite fields work, and I hope that makes some sense. So I hope that made some sense. I know it's a lot of information, but I think it provides a good foundation. If we can understand the motivation behind why things are the way they are, then we have like a solid, rock solid foundation to build off of. So anyway, thanks for watching. The next video will be either on more Cairo stuff or maybe the Ethereum merge or something like that. So let me know if you have a preference. And again, thanks for watching, and I'll see you in the next video. Peace.